instrumental color measurement. So we started this by learning that for us to see as humans color, we need a light source, we need an observer, and we need an object. And spectrophotometers actually have those same three components. So this is our Vista instrument, some of you may be familiar with. And if we looked inside this instrument, we would see that there's a light source. For us, we might look at this sample or a sample under what's called D65 sunlight, right? Full spectrum. Vista uses LEDs to mimic D65 full spectrum. So it has a light source. Now, as an observer, we use our eyes and our brains to look at the sample. The instrument has grating and detectors and computers in it. So it has an observer. And then, of course, the object is the liquid that we as a human can see. And also the instrument is looking at, right? So instruments mimic or have the visual observing condition met in that they have a light source, they have an observer, and they can see and evaluate an object. So we'll look at that in a little more detail. And for all instruments, there's two basic types of measurement methods. That's transmission method measurements and reflectance measurements. So the upper diagram here shows transmission, where light is passed through an object, and the bottom is a reflectance measurement, where light is reflected off or from an object and then analyzed. But in both cases, all spectrophotometers have the same components. They have a light source, they have a collimator that collimates the light into a monochromator, in this case the prism, which then breaks the lights up, or the light into its constituent components, into a selector. And then the wavelength selector selects the wavelength that we want to use to measure the sample. And at the end, we have a detector and the results output to a display. Same for both reflectance, transmissions. All spectrophotometers pretty much follow along the same lines. So here's actually an image of one of our spectrophotometers. So again, we have a light source in the back that's shining the light into a collimator, and that light's that's collimating the light into this monochromator, which is breaking the light up into its constituent components into a wavelength selector. And then that wavelength selector is allowing either one wavelength or multiple wavelengths of light to pass through the sample and onto a detector that literally is basically counting photons, right, at each wavelength, or at different wavelengths. Now, this is a picture of a reflectance optical system. So this is showing a light source illuminating a sample at 0 degrees, and our sensor or optic pickup is viewing or looking at that light at 45 degrees. Very common, 45, 0 and 0, 45 are two of the most common reflectance geometries for instruments. And this is a little closer up of transmittance, where again, light is being passed through and collected on the other side and analyzed. So reflectance and transmittance. Now, where would you use each of these? That's really going to determine on how the light interacts with the sample. So samples are typically going to be opaque, right? Opaque objects. They're going to be translucent or transparent. Opaque objects, all the light is either absorbed or reflected and no light passes through. So these are solid, opaque, no light passes through. And again, all samples either absorb or reflect or both. Translucent objects are not quite transparent, and you're going to get some light passing through, and you're going to get some light reflecting off, and again, some is going to absorb into the sample itself. And with transparent objects or samples, pretty much all of the light passes through the sample. And you get some first surface reflection, scattering, but for the most part, all the light is passing through. So if I have a transmission instrument and I'm measuring something opaque, I'm probably going to get a result that just looks black, right? So these are the mediums of light and how the light interacts with the objects that determine what type of geometry or what type of measurement method you're going to use, reflectance or transmittance. Now, for reflectance, for opaque samples, reflectance is always required, and for semi-opaque or translucent samples, reflectance can be used. Typically, anything that is 30% transmittance or less, right? Less than 30% T can use, it's possible to use reflectance. It's possible to use transmission on, again, the translucent samples that are above 30% transmittance, but required on transparent samples. You must use transmission on transparent samples. And at the end of the day, measurement, the instrument takes the measurement, whether it's in reflectance or transmission, and sends the results to an output. Now, that output could be a display on the instrument. In this case, we're looking at one of our software packages called EasyMatch QC. And it outputs in the form of something called LAB. You can see here on the screen, we have some numbers, numeric results, LAB. We have a spectral graph that shows the distribution of light from through visible space. But you might say, LAB, what in the heck is LAB? Go ahead, ask the question. What is LAB? So LAB was originally invented by Richard Hunter in 1942. Hence our logo, original logo, Hunter Lab. Hunter Lab, the lab doesn't stand for laboratory, it stands for LAB color space. So Hunter Lab, back in 1942, Richard Hunter started this company. He was the inventor of the LAB color space, and LAB color space works a whole lot like GPS, right? So if I asked you to drive from, let's say, where I'm located, or let's say a corporate office, right, in Reston to Chicago, well, you probably have a good idea that Chicago is west, and so you could probably get on the tollway and the freeway, and you could get yourself to Chicago, right? But if I said I need you to go to 422 Michigan Avenue in Chicago, you need a little bit more detail, wouldn't you? So that's where GPS comes in. And GPS, a series of satellites that triangulates locations on Earth. And with GPS, you can find an address anywhere on the planet to within about a 3-foot circumference. That's pretty impressive, right? LAB color space works very similar. It's a 3-dimensional model that ascribes specific values to color based on its color attributes of lightness to darkness, green to red, and yellow to blue. So if we break that down a little bit further, again, the L value, lightness to darkness, ranges numerically from 100 at the top, which would be pure white or pure light, to 0 at the bottom, which is pure black or pure darkness. P value ascribes the color location along the red to green axis. So your minus 100 green would be pure green, up to plus 100 on the red side or A side would be total red. And the same for your yellow blue. Minus 100 B value would be total blue, plus 100 B value would be total yellow. So using this model, we can actually measure these 3 samples of red that we looked at earlier in the spectrophotometer, and we can actually place those or ascribe those colors 3-dimensionally and convert those to LAB, right? So in 3-dimensional color space, each one of those reds has a very specific address. This red is this address, this red is this address, and this red is this address. So like GPS, we have now ascribed very specific addresses for color, and those colors can only be those addresses. So that brings us back to our original dilemma here, visual. Now it solves that problem, right? So Anna receives the color measurement data and says, you know, I got the color measurement data and it's not right. And then Paul down here says, thank you, I see exactly what I need to do to make an adjustment. And instead of sending samples back and forth constantly, we can just use LAB to make those adjustments, and it gets us there to the right color much faster, right? Just like GPS gets us to an address faster, LAB gets us to the address of a color much faster. Now, there are other color scales that are used. So LAB, you may have heard of LAB and CLAB or CIE-LAB. And the difference between the two is that ever since 1942, or since LAB was invented by Richard Hunter, that model has improved. The CIE is the International Commission on Illumination. They're the internal authority on light, illumination, color space. So they're the industry standard, right? They have 8 divisions that range from vision and color to physical measurements, etc. But CIE ascribes color or helps us to better relate how we perceive color, simplifies color understanding a bit more, helps us improve communication, but also better represents uniform color difference in color space. And in general, LAB and CLAB are perfectly acceptable and descriptive for color measurement. However, there's also numerous specialized color indices that are used, and some examples would be the APHA color scale. So APHA stands for the American Public Health Association, and it's used to assess the quality of liquids that are clear to yellowish. So there's an actual scale from 0 color, being distilled water, all the way up to APHA 500, which would look probably something like this very, very yellow vial here in the middle. But basically, this color scale is looking at the color using just a single wavelength, okay? There's another example is CUMSA, which is the International Commission of Uniform Methods of Sugar Analysis. And this looks at the color of the sugar samples at only the 420 nanometer wave. So our instruments are capable of looking full spectrum at color using LAB. We can also help our customers to meet some of these other international standards and indices. Some other examples, there's a coal color index for powdered brown coal. Who would have known? Kent Jones flour color. Specialty Coffee Association, we have an instrument actually designed just for the measurement of coffee, or color flex. And United States and other, Japan and China and EU, Pharmacopoeia, which is the regulating bodies for the pharmaceutical markets. So before we move on, last thing I want to talk about is surface characteristics and how the surface of an object can change our assessment of that color, right? So smoothness and gloss will make the same color on two different objects look different. To understand that, we need to understand a little bit about reflectance. And the law of reflectance says that the incoming angle of a light ray, or the incident angle, is equal to the outgoing angle of the light ray, which is the reflectance angle. Theta I is equal to theta R. Now, when surface imperfections are smaller than the wavelength of incident, like a mirror, then all of that light reflects specularly and perfectly or equally, right? So when that happens, you always get an image, right, like you do in a mirror. So let's kind of look at a practical example. If we look at this lake, up front, we see very smooth water, and what we're seeing are the specular reflection of the clouds in the sky, because the water is very smooth, almost mirror-like, right? However, sorry, jumping ahead, so that would be specular reflection. Diffuse reflection is more common, and it happens when your surface is rough or textured. And in this case, the incident light ray scatters. It's diffused, right? It goes everywhere. It's not equal the diffuse reflection is not equal to the incident ray. And again, looking back at our image here, we can see this in real life. The water in the background is choppy and textured, so we don't see those nice images or reflected image of the clouds. What we see is just kind of a diffuse version of that, right? So we have specular reflection, smooth up front, and we have diffuse reflection of light, which is the choppy water in the back. And this is another example. And actually, our salespeople have used this to help customers understand the surface characteristics of their products. This is a plastic plaque. It's about the size of a piece of paper, and it's uniformly pigmented. So it's the same color all the way through. However, on one side, you'll see that it's been manufactured or injection molded with different textures. So we have coarse texture, we have a smooth matte finish, a semi-gloss finish, a high gloss finish, and very fine texture. Now again, it's all the same color, but this gives an example of how the surface appearance will change how you perceive the color, right? So coarse texture, fine texture, they look a lot lighter, right, than a matte finish. The semi-gloss and the high gloss, they look a whole lot darker and a whole lot deeper, right, richer red. So this is a great example of how the surface texture of a sample or an object will trick your eyes into perceiving the same color as different. So where would our customers use directional, right, 45-0-045 geometry instruments versus transmission versus diffuse? So our customers who manufacture products that want to ensure the color quality of that product meets their expectation of what they want us to see, right? They're going to use reflectance 45-0-045 because that captures everything from the color to the surface appearance. So this is important to use when we want to make sure the color we're putting on the shelf or the color of the labels of the product we put on the shelf meet what we expect the consumer to see from a color standpoint. Now, there's another geometry, diffuse geometry, that can also look at a color irregardless or irrespective of the surface appearance. So we can look at what this color looks like, including or excluding the surface appearance. And that's used in things like formulation, where I'm trying to get to a specific color. I don't care about the surface texture. I just care about the color itself, right? So we have instruments that allow customers to look at the sample, looking both with surface texture and without surface texture. And finally, transmission measurement is always, again, used when measuring solids or liquids that are transparent or translucent.